Welcome to yet another exciting educational video brought to you by Upvision Concepts Academy. So in today's lesson, we'll be looking at IGCSE Physics, and we'll start off with this topic, scientific method and experimental designs. So what are we going to learn today? We'll first of all be able to explain what scientific method means and why it is used in physics. Secondly, we can describe the main steps scientists follow when investigating a question. The third objective for this lesson is design a simple experiment with variables that can be tested and controlled. Fourthly, we can identify the difference between independent, dependent, and controlled variable. And lastly, not on the board, but lastly, recognize sources of error and how to make experiments more reliable and valid. So sit tight. If you're here to subscribe to our channel, kindly subscribe to get more scientific video as we proceed. Okay, so let's look at the conceptual explanation. What really is the scientific method? How do we perceive it? Physics is not just about facts. It's about figuring how things work through observation, reasoning, and testing. So this scientific method we're talking about is the structured way scientists explore questions about the world. So there are actually steps for us to structure these questions. Steps of scientific method, of the scientific method. So it's not just about doing random experiments. We need to have a structured way to be able to find out or discover or explore the world. The first step under these structured steps is observation. You agree with me that scientists will start by observing, and observation just actually means noticing something, either through your senses, your eyes, your smell, your nose, your taste, your mouth, your skin, your feel, how you feel it. So perception is how observation is described. Okay, so example of observation is a metal rod that feels cooler than wood, even in the same room. So you have wood and metal rod. You see that by feeling, you see that the metal rod is cooler. Okay. Second step after observing is that you question. So this is the question stage. You have to question. Is asking testable questions. So you ask, like for instance, so the analogy of metals. Say, do metals conduct better heat than wood? So you ask questions. So the third step in this structured approach is hypothesis. Okay, so with hypothesis, you are actually making an educated guess. So you are guessing. For instance, metals conduct faster than wood. You just guess. So this is hypothesis. Okay, but we are still trying to discover something. So we are going through this process. So the fourth one on this structured approach is the experiment. This is where you actually go all out and test what you have observed, or your questions and your hypothesis. You do the experiment. You test your hypothesis in this step by changing one variable. So you have variables. Example is measure how fast heat travels along metal versus wood. So the fifth step under the structured approach is data collection. So this data collection comes from the experiment. After doing the experiment, you need to record your measurements carefully and collect them. So example is you record the time for heat to reach a certain point. So these are parameters that will come out from your experiment. Data collection. After you have collected the data, you do an analysis. So analysis of that data. Okay, so you have to be good with numbers, have to be good with mathematics. Here you are interpreting the results that came from this data collection. You interpret the results. You use tools like graphing, average equations. So like I said, this is where your math skills is really tested in physics. Okay, so example in analysis is comparing times and drawing conclusion. The seventh step in this structured approach is the conclusion. Okay, conclusion. You are concluding the experiments, but that is not the final step. Conclusion states what your results mean. It states what your results mean. For instance, metals are better conductors than wood. This is where you have come to the conclusion, and you have done all your due diligence, and you are concluding that yes, metal is better than conductors, for instance. Sorry, they are better conductors than wood, for instance. But like I said, this seventh conclusion, seventh step, is not the final approach. You have the evaluation. Evaluation comes after everything has been done. Evaluation. Okay, so here, what you are looking at, you are reflecting on accuracy and improvement. So you are reflecting on accuracy, having gone through this process, how accurate it is. If I can do this experiment again, am I still going to get the same results? So you reflect on the accuracy, and then you see where you can improve. So we can interpret to reduce random error. Okay, so I'm going to just put a cycle. This actually forms a cycle on the board, and you see how it goes. Okay, now so we have the cycle starting from observation, then you go to question, you go to hypothesis, you go to experiments, you go to data collection and analysis, then conclusion, evaluation, and again observation. So the scientific circle shows that experiment can be repeated. It can go round and round and round. So we look at the variables in an experiment. So we have the independent variable, you have the dependent variable, and thirdly, you have the control variables, Okay, so what are actually independent variable? By definition, independent variable is what you deliberately change. So this is what you deliberately change, So this one can be changed. You understand? It can be changed. It's independent. When you change it, it's a new value that you are seeing there. But the dependent is actually what you measure. So this is what you measure. So this one actually now depends on this. So when you change a parameter, for instance, now you will be measuring something new. We'll see that in different things. I'm trying to define this now so that when we start doing the experiment or using the terms, I'll be pointing out a term, independent or dependent variable. For instance, let me just go ahead of myself. If I have this as y is equals to mx plus c, I'm sure you know that this is equation of a straight line graph, linear equation, because the highest power of the variable x is 1, right? Okay, so this actually outside y is the independent variable. The dependent variable. Why this one is independent variable? This one is the one that I can be changing, but I'll be getting a value of y, for every corresponding value of x I'm changing. So this one is independent, while this one is dependent. Okay, but let's just leave this one first. So the control variable is what you keep the same. So what you keep the same. You can also call it the constant. It does not change. Okay. So example for this the independent variable, the material type. You understand? Material type. So example. Let me just put this under here. Example. I can say material type. So I have if I'm doing an experiment, I say I have metal or wood. So the material type is independent. Why the dependent for this particular experiment is the time for temperature rise. Time for temperature rise. temperature rise. So I can decide to say, okay, I want to measure the different times where temperature changes. So I measure in 5 seconds, I check the temperature change. I measure another 10 seconds, you understand? All these seconds I am measuring, they are the dependent variable. They are the variables that changes by my introduction. I introduce it and it's there. It does not depend on anything. It just is a fundamental variable, you understand? So, but this one now depends on what happens, what variable I'm bringing in this place. Okay, so finally, the control variable is the length of rod. The length of rod. So, for instance, the rod does not change that. Rod length, temperature source. So, I must make sure that my source of temperature is constant. You understand? Thermometer position. All these things. Thermometer position. All these things are examples of control variables. Okay. So we're going to the next fundamental, definitions. I have qualitative and quantitative data. So what is qualitative data? So qualitative is actually description. Descriptive. Okay, the word descriptive. So you want to describe something in physics. E.g., the surface became shiny. E.g., the surface became shiny. Maybe you see this from an observation. You observe this, and you now start saying, "Oh, the surface is shiny or became shiny." This is description. You are describing what you are seeing, what you are observing. And the qualitative has to do with everything in science that has to do with description, describing. So you have to have the power of observation to be able to describe, and the power of use of language when you are describing. Okay, so that's qualitative. But for quantitative, all right? All right, so for quantitative, we are looking at numericals. We're looking at numbers. So physics or sciences you have to have a numerical strength, mathematical strength, and also descriptive strength. So numerical under quantitative. So e.g., the temperature increased by 5%, or by 5 degrees Celsius. Okay, so e.g., the temperature increased by 5 degrees Celsius or 10 degrees Celsius. Note that this quantitative is not you saying, writing this language, the temperature. You understand? But what it means is that you are putting a value, a numerical value, to what you're describing. So the difference is that for qualitative, you are describing without necessarily introducing a figure or anything. You are just using the power of your description to get that description across. You are using the power of your description to get how you are observing. You understand? Your power of observation. Meanwhile, for the quantitative, you are actually telling the story with numbers. You are putting the numbers. And I want to advise that you need to also be very good in units, fundamental units or derived units. So in physics, you don't just put numbers, you have to put units. If you are putting distance, for instance, you are putting meters, 10 meters, for instance. If you are putting mass, for instance, you are putting 100 kg. So this also goes with what you are describing in a numerical sense. Okay, so I have a worked example on the board. So for example, if a student wants to test how the length of the pendulum affects the time period. So the pendulum looks like this. It's like a length of string, and there's a bob at the bottom, at the end of this string. So this is the length of the string. So I just put my dimension in here and call this L, length. Length. I'm measuring the length of the string. Then there's a bob attached. So there are two things that come to my mind. I'm seeing length and I'm seeing mass. I'm seeing mass. But if the students wants to get this experiment go through, the first thing you have to do, step one, is to define the variables. Step one, define the variables. We talked about variables not quite long. The variables. So if I have the independent variable in this case, should be what? I want you to say it. The independent variable in this case should be the length of the bulb. Why? Because the length of the bulb is something that you give per instance. You are giving it, it's not dependent on anything, it's independent of itself. So if, for instance, I'm going to take 5 readings, I will say at the first instance, my length should be 10 cm, just for instance. And at the second instance, my length will be 20 cm, and the third instance, my length will be 30 cm. At the fourth reading, it is 40 cm, and at the fifth reading, it is 50 cm, and so on. Each of these instances are independent. It's just a value. You know, the quantitative value there is 10. So it will be 10 throughout that instance of measure. That is why the independent variable in this case should be the length of the bulb. The length of the pendulum, I beg your pardon. The length of the pendulum. So this one is independent. So I'm defining the variables. So for this case again, the dependent variable will be the time to complete the swing. Dependent variable is the time to complete the swing. What am I talking about here? This experiment, the essence is to, let me take this measuring off, take this one off. So this is the length of the bulb. I fix it on this immovable structure, just fix it. So the essence is to determine the time to complete swing. So I take this bulb to this position. So let me just draw a hypothetical position here. So I take it to this position, then I release it. When I release it, it swings like this and swings back. So there's another point where it stays stagnant before it comes back again. So it swings to and fro. So I'm measuring the time it used to swing. This time I'm measuring is dependent on the length. Hypothetically speaking, I know I feel at this point, I'm using the word feel now because we have not concluded the experiment. I feel that, I suspect, yes, that if the length is long, the time for it to swing will be different from if the length is shorter. The time will be different. But we want to investigate whether is it a faster time or a shorter time, depending on the length of it. So the dependent variable here now is the time to come. So that time now depends on the length. That is why we call it the dependent variable. Time for one complete swing. So in physics, we like to denote it with a symbol. So this is T. This is T, while this will be L. That will be L. So the third one I want to identify is the control. The control. Now, for the control variable, we need to ensure that the mass of the bulb is constant. I will not, for one instance, do a 10 kg mass. Let's say, I wrote different instances of the length. I wrote that, for example, I wrote different instances of 10 cm, 20 cm, and 30 cm, and so on. These are different instances of the length of this bulb, of this string. So if I am using 10 cm instance, I will not come and say the weight of the pendulum of this bulb is 5 kg, for instance, and I come here and I make it 10 kg. If I'm changing this thing, it will also affect the experiment. So the control variable, I should ensure that the mass of the bulb is constant. So one of the control variables is mass of the bulb being constant. Okay. Second one, this is how bulb is spelled. Second one is the amplitude of swing. Amplitude of swing. These two must be the same. Must be the same. I should just ensure that this amplitude just means the distance between, I just take this to this point, so understand. So I make sure it's at that point and I leave it. Understand? And it swings. So the amplitude too should be constant, and the gravity should be constant. Of course, gravity is constant. Gravity is constant. I'm doing all my experiments on Earth. I will not come and do the first instance on Earth and go to Mars where the gravity is different. So that's very obvious, but the gravity too is constant. Okay, so we have looked at step 1, defining the variable. So I've used this scenario to explain what independent variable is, again, practically, what dependent variable is, and what the control variable is. I've used this instance. There can be other instances where you see another experiment and you see another aim, and you need to also identify what is independent. Understand? What is independent, does not change anything, and what it depends on the independent variable. Understand? And what should be controlled or constant. So with this explanation, I'm sure you are able to get it. So the next thing I want us to talk about is the hypothesis. For this particular experiment, I will say that as the length increases, the time period also increases. Meaning that if this length is longer, you understand, if it goes longer, the time will also be faster, you understand. But if it's short, the time is slower. That is the hypothesis. So as the length increases, the time period also increases. Okay, so what is my plan for this experiment? My plan. So I'm going to be using 5. I'm going to be using 5. Let me take this off. So for my plan, I'm going to use lengths 20 cm, 40 cm, 60 cm, 20, 40, 60, 80 cm, and 100 cm instances, you see. So this is the independent variable. So I'm going to be varying my lengths according to this. So at 20, what oscillation am I getting? Oscillation period am I getting? At 40, you understand, and so on and so forth. So the next thing I'm going to do, I'm going to measure time for 10 swing and divide by 10 to find average. So I'll measure time for 10 swings. 10 swings, then divide by 10, okay, to find big T. This capital T is the average period. The average period. Okay, so this is straight enough. So what I should be expecting as the relationship is that T is equals to 2 pi, then square root of L over G. Okay, now at this point, we said that gravity is constant. So gravity is a constant value. Gravity, G, is 9.8 meter square. Okay, so that's acceleration to gravity. Then 2 is constant, is a value, and the pi is also constant. Pi is constant. So pi is 22/7. That one is also constant. So, but what is changing is this time and the length. So we said the length is independent variable. The length is inside the equation. You understand? But if I bring out this equation, like I said, you have to be very good in mathematics. Okay, let me take this side off, or let me take this side off so that you can use this side. So if, for instance, now I want to do this, I will say that time is equals to, I'll bring out this constant. I'll bring the constant out. 2 pi, then this another constant is square root of G. You understand? And I'm now leaving this one here, L. This formula is the same thing as this formula, but I've arranged it in a way that I can clearly identify the dependent variable, independent variable, and the constant. So this is the constant. This is the constant. This is the constant. And this is independent variable, and this is dependent variable. So T depends on what is happening in L. Like I said, you see, when I said I'm varying the length for different instances, for the first instance, if I put 20 cm and do the experiment and take my period and everything, do my experiment, what I'm going to be getting as T will be different, will be depending on this 20. So if I change this 20, this L, 20 to 40, my T will also be affected by, or be dependent on 40, and so on. So, but you know that there's a constant term here. So you know that the general formula for linear equation or equations generally is y is equals to mx plus c. Now, this x maps into this one. This one maps into this one by comparison. This one maps into this one. Y maps into t. You understand? And the this one, coefficient of the variable is this guy, the gradient, maps with this. There are sometimes where we have intercepts. You understand? For this one, we don't have an intercept, but there are sometimes when we have intercept. So that one is also another variable that we'll talk about. But they are also control variables. So this is a control variable, this is a control variable. And for this case, I have this control variable here, which is the gradient of this particular line graph. Okay. Okay, so so by the time we do our calculation, if for instance we use L is equals to 40 cm. Okay, let me put it in the calculation. Let me put a calculation there. Take this one off quickly. Okay, so if, for instance, now I say sample calculation for L. So for L is equals to 40 cm. So what will be my T? So this T, which is the period, is equals to 2 pi square root of L over G. Now I'm going to calculate using this one, but first of all, I will convert this one to the fundamental units. That is 40 cm. 40 cm divided by 100 will give me 0.4. So I've converted it to meters. That's what I mean. Sorry, meters. Okay, so when I put this one now in this equation, T will be equal to 2 times 22 over 7, then times square root of L is 0.4 and gravity is 9.8. By the time I compute everything, this T, when L is equals to 40 cm or 0.4 meters, T will be equals to 1.27 seconds. So this is how you do the math. So you should have numerical mathematical strength and also the analytical strength, how to analyze something. Okay, so but everything comes from foundation. The foundation is understanding. Understanding what, for this case, independent variable is, what dependent variable is, what the control variable is, how this maps into a physical, a mathematical expression. This is not just the only experiment there, but I'm using this for an example to describe how all experiments can go. So every experiment, you are expected to identify these variables, expected to also map these variables into an equation, also expected to get quantitative values by calculation. So we're going to sum up by doing a wrap-up of what we have done today. We'll look at what we've done. We start by saying that science begins with questions, not answers. So we start from the questions and arrive at the answers. And the experiment must be fair. So meaning only one variable will change. Okay, so that is the independent variable. So that one will change. Others will, the dependent variable will change due to the dependent variable changing. You understand? So only one variable will change. There's a constant, and the results are more reliable when repeated and averaged. Okay, so we need to also know that you need to repeat the results and get the average. Finally, physics depends on measurement, precision, and critical thinking. Three things: measurement, precision, and critical thinking. Measurement is what you get from your measuring instrument. You understand? Then precision is that you should ensure that you repeat it and get the average. And critical thinking is to ask questions, to analyze, to do data analysis, and get your final answer. So I'm going to be leaving some comments on the comment section. The comments will be like questions and maybe possible answers for engagement. So please visit the comment section for this. Also ensure to like the video and subscribe to ensure that this video gets to a wider reach. So I hope this video has been informative for you. I'd like to thank you for viewing.